Okay, let's get started. Just a quick review of glacial erosion that we talked about last time. We have a glacier in a big main valley and tributary glaciers feeding into it. And that main glacier is chopping off spurs that come down and truncating them, and they're truncating them with triangular facets. So these are big keys that a glacier has been through here, as well as the U-shaped valley. And that chopping off of the spurs also chops off the streams, and it leaves hanging valleys. And we also have arêtes that develop where one of three different things are going on. Cirques eating away at their head walls, eating back and creating a narrow area in between two cirques that are eating toward each other, or a U-shaped valley that is eating toward a cirque, or a U-shaped valley between a U-shaped valley and another U-shaped valley. And the horn, we have cirques coming at an area from 3 or 4 different directions, and we'll leave a nice little peak in there for a while. Okay, so we talked about earlier that we have what we call erosional regime, and that's basically what we're talking about. That's where we erode material, pick up material, and transport it. And we have material that's falling on top of the glacier, as well as being picked up from the bottom and eroding. So in the cirque, we are constantly deepening and widening the cirque. And the U-shaped valleys, we're also doing the same thing. We're deepening and widening with time and successive glaciations. So then the depositional regime down here is kind of fun, and Colorado's got some wonderful examples in the depositional moraines. So let's get going. The plucking and abrading comes down from here, and the depositing and of that plucked and abraded bedrock is out in the area in front of the terminus or snout of the glacier. So remember I said that conveyor belt, that glacier is always moving downhill. Even if the snout is retreating up, it's still bringing material with it. And if it's standing still, if the terminus is not moving either up or down valley, that conveyor belt is still working, and it just dumps the material at the end of the glacier. And it's not very organized, as you can see from this glacier here. This is glacial ice in here, and you can see all the rock on top of it and material that's been deposited here. This is a pretty rock-rich glacial portion here, and you can see rock-rich areas further back. And it dumps all this material, and it doesn't sort this material out. By contrast, the streams coming out of the glaciers, which we'll talk about later on, but streams are very efficient at sorting material by size and by weight. And that's why you want to look for gold in a stream valley, but not in a glacial deposit. So you can see all the material that can be carried on the surface, and that also is carried in the ice, as we mentioned. This is up in Alaska, obviously not in Colorado, but this is in Colorado. This is glacial till. And glacial till, the definition of glacial till is that it is a deposit, a sedimentary deposit, directly from a glacier, not water involved in it or anything like that. It was just dumped right off the edge of the ice, or the ice may have wasted down and melted underneath a layer of debris, and that debris is left on the surface once the glacier is completely melted. So in this deposit, you see lots of different rock types. This one's different from this one. This one is different from those two. And this one is different. Wow, this one is different. So we have many, many parts, many different rock types. They all really tell us a lot about where they came from. And so if we know where this glacier came from, we can get an analysis. And I know I was looking in an area around Durango, and I saw this pile of rocks that have been put in there. I picked out a bunch of igneous rocks and laid them on the ground, snapped a picture and sent the picture to Professor Gonzalez at at Fort Lewis College, and I thought this was part of the glacier that had come from up in the San Juans. And I said, can you identify where all these rocks came from? He said, yes, they came from the La Plata Mountains, which really sort of threw me initially, but as I looked at it, that was completely logical. So telling where these come from can be very important. And in fact, in Canada, in studying the glacial till there, they found little indicator minerals in there that occur with diamond deposits. And using the glacial debris and tracking down where those were coming from, Canada has now produced billions of carats of diamonds as a result of that exploration tool of just analyzing the till and figuring out where it is. It's also been used in Canada to find gold deposits. So here's another Colorado example down by Clear Creek Reservoir. And the main point here is that we have very large materials and fairly angular, along with quite rounded material. And here at the base of this exposure, we have sand that has been washed out of that. So within that bank there, that deposit, you have everything from that huge boulder down to very fine, even silt, smaller than sand-sized particles. And within those, we talked about the glacial till stones before. This is a wonderful sketch from an 1894 textbook on glaciers, the Great Ice Age. And you can see the very different orientations and different depths of scratches. This is the one that we saw before, and you can see the deep gouge at the yellow arrow and the little accumulation of fine ones at the red arrow. And if we expand that area, you can see a little bit clearer the different orientations and the different nature of the different little scratches. And the area down below, the same sort of thing. We have all kinds of orientations and all kinds of different depths of scratching. This is a 5-foot long boulder east of Leadville, and you can see the scratching on it, and it's fairly polished and fairly rounded. And another big till stone, we call those stones that are scratched and polished till stones. But I love till stones and I love looking for them, and I looked in a lot of moraines in Colorado, and they're not easy to find. Okay, I wanted to go over some technology that we've got in the 21st century that really enhances our ability to understand glacial deposits and all of geology, and just to make you aware of them if you haven't seen them. And they are Google Earth, LIDAR, and cosmogenic radionuclide dating. So this is a Google Earth shot. And the nice thing about this is I was curious what the Athabasca Glacier up in Jasper National Monument, I was curious about how it had retreated in the 50 years since I visited there in 1974 with my family. And we parked down here and walked a short way to get to the terminus of the glacier. So in a very quick motion, or very few quick motions on the computer, I can be at the Athabasca Glacier in Canada, and I can study it in a whole bunch of different ways. And here's a nice little lateral moraine along here that you can see. There's another one over here going up here. So it's very, very useful for studying glacial features. And you can place geologic maps on top of the topography that you have in Google Earth, and you can make those transparent so that you can see through them. And the really nice thing about Google Earth is you can spin it around and take any view that you want. And you can zoom in on it, such as this little feature right here. Let's take a close look at that. And there it is right there. And if we want to see what it looks like from the other end, we just spin it around, and here we are looking at the other end and looking the other way. So this has been just absolutely fantastic for geologists, and I use Google Earth every single day. Map view by the USGS is another wonderful advance, and it used to be that if you wanted a map from the U.S. Geological Survey, you had to figure out what was available, find all the details of it, and then you might be able to do it by phone call, but you usually did it by mail, and you sent in a check for the amount, and you waited 2 or 3 weeks for it to be processed and get back to you in the mail. And believe me, that was a long, long time. And here is the state geologic map shown here. And you can see there's the Utah geologic map right next to it, and the Nebraska or Kansas geologic map, and the Nebraska geologic map up here right next to it. So you have these large scale maps, but you can set the scale that you want. So I say I want to see all the 1 and 7.5 minute quadrangle maps in the state, and here they are. And if you want one of them, you can click on it. There's a way that you can download it, and you can have it right away. And I use this very, very often, thanks to the USGS for this wonderful resource. Okay, so LIDAR. This is prior to having LIDAR, the topography that we got was from, we had to fly low-level flights across the topography and overlapping the photographs that we take. And then we would put two of those stereoscopes, right, two of those images together, and they're overlapping, and we'd use what was called a stereoscope, and we could see it in 3D, and that was fantastic. But they were usually in black and white because color was so expensive. Eventually, they moved on to color. But there was one really big problem with that, and that was that a lot of the area is tree covered. This is an area southwest of Leadville down here. In fact, this is the county quarry right up here. And so that cover was really kind of difficult to deal with, both for the map makers. So topographic maps, because of the distortion with these photographic images overlapping and because of the tree cover, they were really accurate only about to plus or minus the contour interval, which could be as much as 80 feet. But what we can do, this is Half Moon Creek coming out of Mount Elbert, and we can actually make out with this that there is the end moraine right here. And we can see the lateral moraine going along this side into the terminal moraine, and we another lateral moraine going over here. So we can make it out, but when we look at the digital elevation model made from the topographic maps that were made in the old way, we have a pretty clear outline of what that terminus looks like of the glacier coming off of Mount Elbert. So these digital elevation models were really nice. But here's LIDAR. And LIDAR, you can see the difference in resolution between this one and this one over here. It's just phenomenal. And this isn't even zoomed in on this yet. You'll see that in just a second. So the way LIDAR works is you shoot a laser down and from a low-flying airplane, just like you did photography. But the thing that does this is basically a flying computer, and it absorbs these millions of laser that are sent back, and some of them reflect off the top of the trees or the parts of the trees, but a lot of them get completely through the trees and bounce back up. And you can sort out those trees so that you get what's called a bare earth model. And I'm going to zoom in. You see this area, the rectangle over here in the left one. I'm going to zoom in on that area right here. And this is how detailed you can get. In fact, on the computer, it's clearer than this, if you can believe that. So this is an enlargement of that little white rectangle up here. And the things that you can see here are just amazing. I mean, here's one terrace level. You can see that there's a lower terrace level here and the actual stream channel down here. I mean, it's just an absolute gift to people, to geologists, who try to understand what the surface is doing. And you notice this little thing right here, and this little thing, and these little things over here, they really puzzled me. They're all over the place around Leadville. I couldn't figure out what they were. And it turns out that they are in-ground charcoal kilns. they would dig a trench about 10 feet deep, 30 feet wide by 70 to 90 feet long, put logs in there, set them on fire, and cover them with dirt, and turn it into charcoal. And this was a huge industry for Leadville prior to the time that railroads came in and they could bring coal in. So at one time, there were 5,000 people in the Leadville area that were working in this charcoal industry alone. Okay, the other thing that's kind of neat is this national map viewer. You can get topographic scales. As I zoom in, it's going to change to different details of scales. And so you no longer have to buy a topo map. You can just pick the area you want, zoom in, and do a screen grab, and you've got a topo map of what area you want. You also have this digital elevation model underlying it. If you check this little place over here when you're in these layers right here, this is what it brings up. And all of the LiDAR that's available will show up when you zoom in on this. So you can get, this is the best place to really view LiDAR without having to download it to work with it or not. So at any rate, enough of that, and on to cosmogenic nuclide dating. One of the things that we've had in the past is to date glacial moraines. We had to use things like lichenometry or weathering, soil profiles, and this sort of thing to try and date the various age moraines. And this cosmogenic nuclide dating, there are cosmic rays that are coming in all the time. And when they hit quartz particles, they alter the chlorine in them and beryllium to different isotopes. And so you can look at, it's assumed that a boulder that's in a moraine is a fresh boulder. And this alteration only occurs in a very, very thin layer on the outer surface of things. So if you've scraped off, as glaciers do in the glacial valleys here, you're going to get the time at which the glacier went away and it was exposed to the sun again. And that's a new exposure to the sun because the old exposure was worn away during the tumbling of the fragments and of the abrasion of the bedrock underneath. So here's a 125,000-year-old date on a boulder here in an older glacier that everything tells us it's an older glacier, but now we know pretty much how old it actually was, and a 21,000-year date here. And that is the date of maximum advance of most of the glaciers in Colorado. And so then we retreated back to here, and this recessional moraine here, the boulders in there give you a date of 15,600 years old. And if we look up in the upper right corner in a cirque, it get 14,000 years ago, and that tells us the time at which this was ice-free and it was open to the sunlight. The red arrow up in the upper right there is at Independence Pass, and this is the Arkansas River down here, and this is Twin Lakes. So this has been a tremendous advance in being able to understand things. Okay, so we've seen this one before. Again, we're not going to worry about it too much, other than we had a tremendous decrease in temperature globally from 55 million years ago. Now, we had glaciers coming in the southern hemisphere about 15 million years ago in East Antarctica. But we didn't have any in the northern hemisphere really beginning until about this time and really getting going in this time here. These are when the Greenland ice sheets began, and then we had the valley glaciers. Not clear exactly when they started in Colorado. If we blow up these are the individual years of data, just give you this fuzzy looking thing to the graph just to sort of explain it. And here we are going into our just before our real ice age, which was down here. Okay, so this is from the Geological Society of America. And again, it looks like a dog breakfast, and I'm going to try to simplify this for you. Over here, we have a magnetic reversal chart, and they've been dated very well, and they're very, very important for understanding the age of various things, but we don't need to worry about them because other people do that for us and just give us the results. And then by the same token, here are different ages broken down of these other things by fossils. And again, I'd never even heard of these words before. I put this chart in the thing here. So we can eliminate that. And we're really left with a much more simplified chart. And so we have the absolute ages from combining the fossil data with the magnetic reversal data and any other volcanic eruption data that we can get. And we have an absolute age of 23.5 million years and going down to 0 at the top. Now, this chart's going to change in your lifetime. It's changed in mine. My PhD thesis was on some volcanic rocks. There were 23.5 million years old in California along the San Andreas Fault. They'd been split by the fault and moved 200 miles apart by the fault. And back then, 23.5 million years ago was Miocene. But now they've moved it up, and so they're Oligocene. The rock's age hasn't changed. It's still 23.5 million years ago, but the classification changes. And the poor Pleistocene up here has been getting condensed on both ends from above and below to where it is now, instead of about 11 million years long, it's less than 5 million years long. Okay, so the Neogene and the Quaternary are the periods that we are dealing with here. And Colorado's mountains were built during this time period and still are being built. So there is a lot of old stuff in the literature. I mentioned this last time, that these mountains that we see today that are so glorious are left over from the Laramide, and that's just simply not true. We have a ton of data that shows that the rough uplifted mountains that we've got were uplifted along faults with kilometers of displacement as block uplifts during the Neogene, most of that in the last 10 million years. There's some people fainting, I'm sure, pulling themselves off the floor. Okay, so we have Neogene and Quaternary as the last 23 million years of Earth history. And the Quaternary is what we're interested in from a glacial standpoint, because that's pretty well defined by that time when it went into the coldest times. And it's made up of the epochs of the Holocene and the Pleistocene. And it started 2.6 million years ago. And of course, the Neogene starts 2.6 million years on back to 23 million years ago. Excuse me, I set my alarm incorrectly there. Stop. Not really. Well, is it? No, it's not. Time for a break. 12 o'clock. Okay, so we used to think about 4 main glaciations when I was learning geology and in affecting the United States. And we now think that possibly there may be 22, as you can see here. Each of these large areas is a major glaciation. The little dashed ones are minor glaciations. And so here's our Pleistocene, Quaternary, the Pleistocene covering this period, and the Holocene's just this little tiny bit. It's the last interglacial since the last ice age melted. That was about 11,000 years ago. And of course, that date, we keep getting new data, and that date has changed and will change from time. And they just voted down last year to start a new period, the Anthropocene, for when humans have started affecting the Earth. And that was voted down last week by the International Commission. Okay, so these are really the only three that we need to really worry about, and actually only these two. So that's nice and it's manageable, and we'll see the details of that sort of thing. Okay, so now people, those of you with color of the hair of mine, you probably learned when you were doing geology that there were 4 glaciations that affected the United States, and they were the Kansas, Nebraska, Illinois, and Wisconsin ages. They were getting, Wisconsin being the youngest. So they discarded all of those ages with the exception of early Wisconsin age. That's the only name like that. They're now going and talking about marine isotope stages, and these are derived, you don't need to know the details about this, but these are derived from the marine being ocean sediments and isotopes within them, and these isotopes give us a feeling of what the temperature was at that time. So like a 013, 018, different numbers will tell us, 016 will tell us supposedly what the temperature was at that time. And this is a breakdown of those going back for the last 500,000 years. And this is also combined with ice core data from Antarctica and from Greenland. I've changed or provided the Fahrenheit degrees in red on the left side over here. And we are looking at the average global temperature, And so we, just for comparison, during some of these, Denver's average temperature is about 51 degrees. And so that would be consistent with an interglacial period's warmth. And Durango is about 47 degrees. And the average temperature in Telluride is 42 degrees per year. And that's close to an ice age temperature. But of course, the average temperature in Telluride isn't the global temperature. So we're not in an ice age, we're in an interglacial. And this interglacial is the #1 marine isotope stage. And all of the all of the interglacials, as you can see, are odd numbers. And then this is a glacial stage, and this is marine isotope stage #2. This was our last major glaciation in Colorado, and MIS2. So we don't need to memorize this, or I'm not going to use it, but if you just see it written somewhere, you'll understand what folks are talking about. So this interglacial, and then we had this little possible ice age right here, another interglacial, and then our major glaciation. So that's all we're going to be worrying about. We can forget about all that other stuff, because these glaciations probably removed certainly 98% of any evidence of any older glaciations than this. This is from a Nature article that did a comparison. This is now percents warmer or colder than today. So 0 is today. This is where we are. Of course, now I flipped it on you so that today is on the left side of the chart instead of the right side of the chart. And this is going back about 200,000 years. And this is the period of time that we see glaciation evidence in Colorado. So you can see that the first one is MIS2. We are in MIS1, and we call that the Pinedale. And it's named for Pinedale, Wyoming. And we didn't use a different name except in one place in Colorado for what was going on in Wyoming, kept the same name for the same type of feature. And this is MIS4, early Wisconsin. And this is a big debate whether we have evidence of early Wisconsin or not. And we'll talk a little bit more about that toward the end of today. And Bull Lake, or MIS6, is a big glaciation that we have lots of evidence for in Colorado. And then we have pre-Bull Lake. So, and one of the things that's interesting about this analysis is that you notice that in terms of temperature, we're like 25% higher than today's temperature during this last interglacial period. And we're nowhere near that temperature in our present interglacial. Okay, so you need to learn Pinedale and Bull Lake. I'm going to be using those a lot, and I'm going to assume that you just instantly memorized these. Okay, so we've got this conveyor belt that we saw before, and it'll pile up material at the bottom as this stuff adds on to it. So if we turn that into a big truck that's got sand or material sliding out of the back of it, it'll pile up at the tail of the big truck. And if our big truck glacier advances back up the valley, it will lay down a pretty uniform layer of debris on the bottom as it moves up the valley. Now remember, all the time that the snout of the glacier is moving up the valley, the glacier itself is continually bringing debris to the end of the glacier. And if the truck stops or the glacier stops in its path, then it'll build up another pile. So till is what the actual sediment that's made up from glacial deposits. The shape of the till we call moraines. And we have a number of different names, obviously, because geologists just love names. Otherwise, you wouldn't have things for our students to memorize for the tests. So here we are. Then if the glacier retreats or stops its retreat and advances again over this stuff that it's deposited, it can completely bulldoze it out of the way or pick it up or pack it down and destroy the material that was deposited as it retreated. So we have, unfortunately, some really good mechanisms for destroying evidence of previous glacial activity. So here's maybe a diagram of what we've got. The dark brown at the bottom is the bedrock in this model, and this darker green stuff is old till that was deposited from an older advance or an older glaciation. We've got outwash cutting through here from the melting of the moraine back there. We might call this older till Bull Lake, and the retreating glacier, because it's melting a lot. There's a lot of water that comes out of a retreating or melting glacier. So our newer till that deposited these two moraines there, we'll call Pinedale. And this is our end moraine. And if that's the farthest down valley, then it's a terminal moraine. So end moraines is a general term for debris that's deposited at the terminus of the glacier or at the snout of the glacier. But sorry about that. I set all those alarms just so I wouldn't go over and we could take our break when it was scheduled, and didn't do a very good job of setting my alarms. Well, good job of setting them and not for the correct time. So these are all end moraines, and one could argue that this ground moraine is end moraine also because it's deposited at the end as the glacier is retreating back. The terminal moraine is simply the moraine that is the farthest down valley, and it's an end moraine, but it may be the terminal moraine, and any that are up valley from it are called recessional moraines. But you go, if I take you and I put you on one of these on a recessional moraine, then I blindfold you and I go put you on an end moraine, you can't tell the difference. Okay, so recessional moraine, we said, was as the truck paused and dumped a little material, and then it got moving again and spread a fairly uniform layer. And this is not just from spreading as the glacier retreats. It also, you can have stagnant ice under that just slowly melts and lays down a layer, like the ice that we saw in that photograph. When if that's sitting in place, if that ice just melts, then all of that debris is just going to be let down where the glacier was. Okay, so memorize again. And what we're looking at is different features in the Bull Lake versus the Pinedale. Now, they didn't have different features to begin with. They both had sharp peaks for them, but think about Bull Lake. The Bull Lake, the important thing to remember about it is it's been around for 100,000 years longer than the Pinedale or more. And so the Pinedale has been subjected to erosion for about 13,000 years. And it hasn't eroded that much. The Bull Lake deposit has been around for about 120,000 years, and it has been subjected to rain falling on it. For the soil profile will be deeper than it is on the Pinedale because it's been subjected to weathering for a lot longer time. And the shape of the Bull Lake usually is much more rounded and not peaked like the Pinedale moraine is. And then we have this older moraine that's got even older soil profiles in it and not much shape of an end moraine or a recessional moraine or a lateral moraine. Okay, so here's a comparison just to look. This is in Dillon Reservoir, up just out from east of Frisco. And this is what the Pinedale moraine looks like. And it's much shallower. The Bull Lake moraine is to the right of it. This is the Bull Lake moraine over here. And you notice that it's very lumpy, and much of the original topography is preserved. Now, why is this lumpy? Well, you saw in that picture where we saw the glacier and all that stuff on debris on top of it, you got blocks of ice under there that are trapped and are melting. The stuff is just dumped. It's not organized in any way, shape, or form. So you get these very, very irregular, what we call hummocky topography on top of there. And in the Bull Lake, you can see there's still some of that left, but it's much, much modified because it's been eroded and eroded. You can see it's got steep, deep little ravines coming off of it here, whereas over here they're very shallow ravines from the water because they haven't developed deep moraines yet. And it's broadened this, made it much more rounded. And this is the area that we were looking at, and this is the glacier. This is the exit to Frisco down here. And this is what the glacier, the Pinedale Glacier, looked like at the time that it was deposited here. And Frisco is right in this area here. The hospital's right up here. Hospital actually sits on a Pinedale moraine. Okay, so here is a map of some areas in the Indian Peaks, and the green is bedrock that is exposed today. The yellow are deposits, and the orange are deposits, glacial deposits in front of the glacier that was coming down those green bedrock valleys. So the bedrock, again, the yellow is Pinedale moraines, and the orange is Bull Lake. And so what do we notice here? Well, we notice that the Bull Lake is generally broader. Those moraines are generally broader than the Pinedale, and they extend farther out in front of it. Because if they didn't, if they were less than the Pinedale would have wiped them all out, and all we'd be seeing are Pinedale moraines here. We wouldn't have any clue for the Bull Lake. So this is the pattern that we'll see over and over again throughout the states. This is just north of Frisco and Silverthorne in the Gore Range as they come down to the Blue River Valley, which is Highway 9 going up to Kremling. And the white are the Pinedale glacial extents and the tan are the Bull Lake glacial extents. And again, you can see the Bull Lake came out farther than the Pinedale did. Okay. So for moraines, these glacial direct creation by glaciers or deposits by glaciers, we've got lateral and which are terminal and recessional. We have ground moraine, and we have inset or nested moraines, which are essentially recessional moraines. And then we have erratics, and we'll take a look at each of those. So here's the till that makes up some of the Clear Creek Glacial Valley. And the eagle is watching, standing on one big rounded boulder that was deposited in the moraine. It's a Pinedale moraine. And this is what these moraines look like. That's where the eagle was sitting, was right down there on the till of the moraine. And within that, you can see these beautiful outlines of the lateral. And the terminal moraine's not very clear here because it actually was wiped out by catastrophic floods, which we'll talk about much later. Here's the LIDAR of that area, of the Twin Lakes area that we saw before. The Twin Lakes area is a wonderful area to study. I counted one time about 70 cirques along 20 miles of the Continental Divide that feed into this depositional area. It's a huge, huge glacier, and it's got lots of neat things. Okay, so lateral moraines are ones that are on the side. We've got recessional moraines where behind the terminal moraine, and we've got ground moraine, sometimes in between, sometimes not. So we have this outer set of lateral moraines, and we have an inner set of lateral and end moraines. And these are from the glacial ice wasting away by melting. And as the ice melts away, it gets narrower, the glacier gets narrower, and it retreats up the valley. And it also gets lower in elevation. So you can see that this lateral moraine here is lower in elevation than the one here. This was what was deposited at the glacier's height. And that's a minimum height for the glacier. It could be higher than this, or could have been higher than this. And then the next one is a little lower in elevation, and we'll see a sequence of this in real life. Now, this is probably the most famous terminal moraine in the world. And generations of geology students have learned about glacial terminal moraines from Turquoise Lake. Most of them have never seen it. And I did. That was me. I learned how to do that in 1961 at the University of Georgia. Well, got plenty of alarms. The alarm's is definitely working. So I had some outrageous statement that I said that generations of geology students learned their first bit about terminal moraines at Turquoise Lake. How can I make an outrageous statement like that? Well, here's how. When I was a freshman geology student, I had an exercise. I took my beginning geology course, and there was an exercise in this workbook that we had, which was called Exercises in Physical Geology. Only mine was the first edition, not the 10th edition. And now there's a 12th edition. And we had to go in and mark and label the end moraines, the lateral moraines, the cirques, the hanging valleys, the arêtes, the U-shaped valleys. We had to label all that stuff. I think I got a C on this or something like that. But this 12th edition, this exercise book has now sold over 1 million copies. And the 12th edition has 9 exercises on valley glaciers, and 8 of them are in Alaska, and the 9th one is still Turquoise Lake. So here's your opportunity to go see the most famous terminal moraine in the world. And it's wonderful, and it's a great example. It's just shape-wise really neat. Oh, the cirques up in the mountains that fed into the Turquoise Lake Glacial Valley to create this terminal moraine. Here are the lateral moraines. So this is just a fantastic place to go play around and look at glacial features. This dam is right here, and I'm pointing this out for a reason, which you'll see in just a minute, which is right now. That dam is right across here. There was a study in the 1880s by the federal government to see where would be a good place to build dams. And there were 9 places in this report done in 1889 to build dams. Now, this is back the Sugarloaf, but this is actually the Turquoise Lake Dam. But at that time, it's called the Sugarloaf Reservoir. And it was 1889. Here is the date on this. They said we can build a dam across here and just have to fill in this area here. And it's about 1/3 of a mile that we'll have to build a dam. And we use 4 miles that nature provided for a dam. And we can build this big reservoir without having spent a lot of money. So there were 9 of these dam sites that were proposed. 8 of them were using moraines as part of the construction to hold back the reservoir, including Twin Lakes, which is right here. Okay, so, well, here we're looking down on this. I'm going to shade the overlay here a bit. And you can see that we've got a lot of detail coming through. And if we look at the LiDAR, here's our lateral moraines that the red arrows are pointing to, very sharp pointed. This is Pinedale now. And we don't have any evidence of Bull Lake here. We do have some outboard stuff that's Bull Lake, but it's not much to look at. So when we look at the top of the moraine, you can see that there are these large boulders everywhere. They're all scattered back through the woods. I think I missed a couple. And if we look up here in the lower right, you can see that there are smaller boulders sticking up and down to pebbles, cobbles, and eventually the whole thing's going to be sand and silt. And because of all the silt, that makes a good clay particles. It makes a good seal and holds back the reservoir. So the lateral moraine coming in and changing to the terminal moraine. Sometimes you say, okay, where is the change from terminal to lateral or lateral to terminal? And nature didn't know that we were going to come up with all these pigeonholes, so it isn't really always clear exactly where that occurs. But notice right here, there's a little pond, and there's a little pond there, and there's one there, and there's one there, and there's one there, and there's one there. This really highlights this. So this hummocky topography that we have here, this is just typical. And when I go look at the continental glacial moraine, I know exactly when we drive on that about 15 miles northeast of me here in Wisconsin, because it's just like this. It's got these little round oblong ponds all through it. It's got these lumpy hills and weird looking valleys. And no consistency at all because it's a big dump. And looking at the Google Earth view of this terminal moraine, there's a larger lake, there's a lake, and here are all these little lakes that are in here that are called pothole lakes or kettle lakes. If they're dry, they just referred to as potholes. And here are a couple you can see up close. Okay, well, let's take our break there and then we'll come back and look at the wonderful Twin Lakes, which showing the great moraines, it says there at the bottom. This is from the Hayden survey in 1870. Good.
Adrian asked, hoping that Dr. Matthews might be able to share some of his favorite or most relevant references for the younger ages of Colorado's mountains after the presentation, perhaps a follow-up email with links to a couple papers, something like that.
Okay, that unfortunately, a lot of that stuff's hidden in kind of esoteric literature, and I've pulled some of it out. Some of it you have to pay for. Of course, if you belong to a university, you can get it. But I'll try to put together a few of the papers that will document that. There are techniques used for that that are quite extremely useful. So thanks for that question. Lou's question about how confidently can you differentiate debris flow deposits from glacial till? Well, the debris flow deposits can have stratification. You're not going to have stratification in glacial till, and also location of where, in the shape of the deposits. And sometimes it's not possible to tell the difference.
Thank you, Vince. I think I caught most of that. And I don't know if you saw the question above that. Very early on in your presentation, you showed a photo of a glacier and you were introducing glacial till. And I wondered what the location of that photo was. It was right at the front end of your talk, and you were introducing glacial till.
Yeah, I don't know where. I just grabbed that. I thought it was somewhere from the internet. I just thought it illustrated.
Maybe Mendenhall Glacier?
Pardon?
It looked like Mendenhall up in north of Juneau, but I was curious.
I don't know. There wasn't any label on it. And so it was one I said, oh, that'd be kind of nice.
No worries. Thank you.
Hi, Larry. Welcome. Thanks. And Mary added that if you find till stones, it's most likely a glacier. And I know, Lou, we've talked about the place that you have these boulders that have scratches on them. But I think Mary in general is correct that if you find those, statistically, they're going to be glacial till, but they're not easy to find, having looked for a lot of them. Okay, so this is just a wonderful place. The Hayden survey thought it was a wonderful place. They talked about the Great Moraines. There we go. They estimated the height of Mount Elbert, 14,351 feet. And that's just a little under 100 feet off, which is not bad because they were surveying from the Missouri River all the way to here. And it's pretty darn good surveying for back then. The maps that they made are just amazing maps, because when they were making the geologic maps, they didn't have topographic maps to start from. They had to make their own topographic maps. Pretty amazing. Okay, so the terminal moraine here shown in this area. Get my laser pointer back. This area here that the black arrow is pointing to, and lateral moraines on the side, and lots of them here, and that's what's really kind of cool. This is today's representation that we can do of things. This is from Paul Weimer's group interactive geology project at the University of Colorado, which unfortunately, now that he's retired, may not continue. So Twin Lakes is just a marvelous, marvelous place. It's scenic. You can look up at Mount Evans on the right. Out of the view of the picture, you have this fantastic U-shaped valley that, as I mentioned before, gathered ice from 70 cirques at least, depending on who's counting. And a hanging valley that you can see here. There's a crest of the lateral moraine up here that's 1,000 feet above lake level. That meant that this whole valley was filled with 1,000 feet, and we'll see what that means for the U-shaped valley that the ice came out of. But when ice comes out of a U-shaped valley like that, it spreads out if it's not constrained. It doesn't stay in a little narrow, locked-in thing. So there's a recessional moraine up there that separates the two lakes, or now a reservoir. Here's the LIDAR of the area, and glacier came down at least to this point. It may have gone farther and may actually have dammed the Arkansas River at one time, but we don't have the record to say that or not. There was a lake here at one time. It was caused by another glacier downstream that blocked this, and the Twin Lakes or Lake Creek Glacier was calving off icebergs into that lake at that time. So this was the maximum extent, and those of you that are familiar with snow mastodon up near Snowmass, the lake that gave us so many fossils, this is a similar bulge that created that lake up there. Okay, so the glacier retreated back to this point, and you notice that there is a beautiful, beautiful recessional moraine shown here by the LIDAR. And then it recessed on back, and it left these wonderful, wonderful landforms that we have. I want to zero in on this area. There's just the inlet. You can actually drive right almost, you got about 50 yards to go to that inlet there. This is all national forest land, so you can go out and experience a recessional moraine. So here, this maximum extent, this is 600 feet above the lake level. The ice was at least that thick here. And if we zoom in on this area right here, you can see that there are all of these little recessional moraines, each one lower than the other as the ice margin retreated from this. And so I counted 20 some individual little inset moraines here that were lower and lower. And of course, we have the recessional moraine back there just down at lake level. And looking along the side, here's a moraine right here. That's the Bull Lake moraine, and that boulder right there was dated for cosmogenic dating. That's where that 125,000 year date. So these are Pinedale moraines, and you can see the difference in the roughness of them on the LIDAR. There's that boulder being sampled for the cosmogenic nuclide analysis. So here's that lake that was dammed by the Clear Creek Glacier down here. And it was 600 feet deep down here and backed up for about 14 miles, former Lake Arkansas. And it failed catastrophically because when the lake gets to 90% of the thickness of the ice, it's going to lift the ice. And guess what happens when it lifts the glacier? It was estimated by folks at the School of Mines, Keenan Lee in particular, and his students, that this lake drained within 24 hours. And it caused catastrophic flooding and depositing of huge boulders downstream, perhaps all the way as Buena Vista. Got to use my Leadville talk, Buena Vista. Okay, so here's this cosmogenic nuclide dating that was done, the Bull Lake moraine that we saw just previously, located right here. And here's this 21,000 year date on the terminal moraine here that's at this point's about 400 feet above the level of the lake. And here's this 15,600 here. So the 14,000 up in the upper right that we saw, we had a 4-mile retreat from this end back to the recessional moraine here. And that occurred in 5,400 years. So then we had a retreat on back to the Cirque, and that was a 16-mile retreat in only 1,600 years. So here's where you have to be kind of careful, because it would be easy to say that the ice was melting much faster during the time period when it was moving, recessing back to here. than excuse me, was melting much slower than it was in the time that we, in 1600 years, melted back 16 miles. The thing that you have to really be cautious about is that at the maximum extent, 21,000 years ago, these lateral moraines along here, right in here, were 1,000 feet above that recessional moraine. So you had a narrowing of the moraine and of the glacier, and you had a retreat back to here, not just in the terminus, but the volume of the ice was getting much, much, much less than what the volume of the ice was when it started retreating. Okay, got this moraines. We're Clear Creek lateral moraines. I think they're some of the nicest lateral moraines in the state. Got very nice. They're about 700 feet high here. This was the one that dammed Lake Arkansas, former Lake Arkansas, and eventually collapsed and was wiped out. And that's why this one has beautiful lateral moraines, but it doesn't have much in the way of terminal moraines because they were wiped out repeatedly. We know at least 3 catastrophic bursts and probably more than that we can document. If you've ever been to Rocky Mountain National Park, you know that the centerpiece of the park is Moraine Park. And guess why it's got that name? Well, it's got this marvelous bedrock knob down here, which has nothing particularly to do with it, except that it kind of stopped the glacier when it came down. The glacier came down this way, and the south lateral moraine down here is about 700 feet high, and the north lateral moraine is about the same thing here. So very, very scenic and very nicely displayed from many parks curve. And right out there in the middle, I'm sure you've all recognized, but if you haven't before, I bet you will now, whoever helped me with that pronunciation of Roche-Montagne. I still don't know what the correct pronunciation is, but that's a Roche-Montagne out in the middle. This is it. This is bedrock. And you can see the abraded valley here, the beautiful lateral moraine in the background, and the plucked end down here. And notice over here at the right end, you notice this little thing mimics that same thing. It's abraded and gently sloping and then plucked on this downside. And you just see these patterns repeated over and over and over. And this is what it looks like on Google Earth. I've outlined the north lateral moraine and the south lateral moraine, Pinedale moraine. The red is Bull Lake moraine. And I've done a cross section through here to sort of take a look at that. This is this B out here, are bedrock knobs. And this is our cross section showing the ice being at least as high as the lateral moraines and the bedrock that's being sculpted beneath it. And there's our Roche-Montagne that was also being sculpted beneath it. Okay, this is a view of the Woods Lake Glacier. If you don't want to register to go see Moraine Park, you can see something I think just as spectacular without having to pay, without having to register, and without having to wait in line to get into Moraine Park in Rocky Mountain National Park. And this is one that you won't find a crowd on, and it's just as spectacular, I think, as the Moraine Park itself, although it doesn't have a Roche-Montagne in the middle of it that I've found so far, but maybe you can find one when you go up here. So here's the end moraine right down here, and you can pick out for yourself by now the beautiful lateral moraines. And there's a recessional moraine here, and there's a whole bunch of recessional moraines between these two. These are all little recessional inset moraines right in here going back up, and we'll see that on LiDAR in a second. Yes, right here. So there's the outline, the extent of the terminal moraine, and you can see all of these beautiful little recessional moraines inside of that. And here is the LiDAR of the eroded valley by comparison to the depositional part of this Woods Lake Glacier. And you can see all of these little features here that are shaped in the down valley direction. Okay, so erosional regime, depositional regime. This little 16-mile Woods Valley Glacier shows it all right here. Here's the erosional regime. That's all bedrock. That's all sculpted, elongate in the down valley direction and plucked in the down valley direction, abraded in the up valley direction. And then where it comes out and starts dumping its debris, you can see this marvelous set of depositional features here. And looking at it in Google Earth, the same thing, the erosional area with lots of little cirques along its side up here, main cirque up here, and the depositional regime down here. Okay, so now for Colorado's most spectacular glacier in the state. And if you look down here at this, I'm honored to have Mary Gillum on this session with me today, and she was very valuable when I started my odyssey of trying to put this book together and taught me a lot. This is Durango down here with the D and Silverton up here. The thing is amazing. Depending on what you're calling the actual cirque, it's 50 to 56 miles long, 600 square miles in area, and it's the lowest glacier that we know of in Colorado. Most glaciers in Colorado didn't get below 7,500 feet in elevation. So if somebody's telling you that there's a glacial feature at 6,500 feet somewhere, you should be suspicious of that. Right off the bat, that right there should tell you, got a problem. And to lose question about, is it a debris flow or moraine? It's probably a debris flow rather than a moraine. But this one got down to 6,540 because it was so massive. This is this was published in 1936 by the U.S. Geological Survey. It's a view of what's called Animas City at that time, but it's just the northern outskirts of Durango. And I wish I'd been there back in this time, or it was still like this, because as you'll see in a moment. This is the youngest moraine. You can see the beautiful outline of it here. That's what it looks like up close and personal, just like a moraine ought to look. And there is another moraine that is pretty much the same age, but it's a little bit older. And there's another third Animas City. And we think that these moraines, these three moraines, the Animas City moraines, are equivalent to the Pinedale in the rest of the state. Unfortunately, the names got changed down here, and so we have this name change issue to deal with. This is the Spring Creek moraine, which is older, and it is 170 feet. The base of the moraine is 170 feet above river level. And so down cutting deeper is operating well here. And certainly from here, here's a Durango moraine, which is a pre-Bull Lake moraine, and it's 400 feet above river level. So we've really got a tremendous sequence here. And unfortunately, here are those moraines again. Oops, okay. This is the Durango moraine, and there's an even older Durango moraine back here, and we don't have dates on them. Here we have the most beautiful sequence of moraines anywhere in the state, and we can't date them because of all of this. It's all been disturbed. Would that we had been back in the time that the USGS took that picture, which was before 1936. So notice the Animas River path back here, and then suddenly it changes to much straighter here. Well, it wasn't straightened through town. It flowed that way through town. And what happened is that this youngest moraine dammed the river and backed up a lake about 11 or 12 miles or so for former Lake Durango. And the river, the Animas River there meanders because it's so flat, because the lake filled in with sediments. And there are cores in here that shows that there's hundreds of feet of sediment filling that up to the flat plain that we see today. You see meandering rivers in the Colorado mountains, you know something funny's gone on, because they shouldn't be meandering here. That belongs on the Mississippi River floodplain. So there's the older Animas City, there's the Spring Creek and the Durango older moraine back up on this is the mesa that the campus is on. Well, there are lots of other cool things with that. And one of them is this arm here, which looks like a tributary glacier coming in. And at the Purgatory Ski Area, we have this really nice U-shaped valley. Well, that U-shaped valley looks like a hanging valley. It's 1,000 feet above river level today, the bedrock level of the valley. And so you go up into that hanging valley, and I'll just give you a quick little quiz. What do we expect to find in that valley? We expect, I think, by now, hopefully you will say, we expect to go up that valley to a cirque, right? Maybe even some tributary cirques or tributary valleys feeding into that. Not. What you find is a valley that is dipping away from the main valley. The main valley's back here that we were looking up at and seeing the U shape there. Ice actually flowed down this valley and deposited, when it retreated, it deposited recessional moraines, a number of them in here. And if we look at the LiDAR in there, there's that recessional moraine that we were looking at with the drone shot there. There's another one, there's another one. And there's a terminal moraine down at the end of the valley instead of a cirque. So think about this now. Over here, you had this ice going down here, and the hanging valley is 1,000 feet above the base of the valley that the Animas Glacier was flowing in. So that 1,000 feet, the ice just kept on going down, and there was probably more ice here than that. But it was so much higher and thicker than 1,000 feet that it just overflowed and flowed down this valley. We're going to see some other examples, perhaps even more spectacular up here at Mullis Pass, which is south of Silverton. This is an area that's kind of fun to me. This is Mount Princeton and the chalk cliffs of Mount Princeton. It's a wonderful spot geologically from a whole bunch of different places, aspects. And these are the chalk cliffs there that are not chalk at all. They're just hydrothermally altered rock. And this is a fault plain essentially right here for the Sawatch Fault that has kilometers of displacement as Mount Princeton was uplifted during the last 10 million years. And that fault along Mount Princeton, or along the base here, along the base of Mount Antero and all the other mountains in here, that fault is in the National Earthquake Hazard Fault of being capable of generating a magnitude 7 earthquake. Here's a Pinedale moraine right here. And the Pinedale moraines in here are really, they're kind of screwy. I have a friend that lives near here that's very interested in this area, and his companion owned a bunch of property back here, and he took me for a ride in here, wanted to show me this, and I looked at all this stuff, and it was just really puzzling to me from a number of standpoints. But here are these little inset moraines you can see. But that's the South Lateral Moraine, and this is the North Valley Wall over here. That white dotted line is on the kind of cliff edge of this plateau up here. And here's the North Lateral Moraine right here. It's out in the middle of the valley where it doesn't belong. And I just, what's with this? And so it was very, very puzzling to me. And this cross section that I drew through it will kind of illustrate that. You can see that the lateral moraines, the south lateral moraine is just like it should be essentially. And the north lateral moraine is this dinky little thing out in the middle of the valley when it should be over here up against the wall here. Well, guess what? This is the Princeton Hot Springs right here. And the temperatures that have been measured in there in Fahrenheit are 140 to 187 degrees. Guess what? Ice melts at 32 degrees. So there's the area of these hot waters, which has been looked at for geothermal development. And so when this glacier came down and hit this hot area, guess what happened to the ice? And so it only was able to reach this length over here, and it deposited these Linset moraines as it retreated, but it just deposited this dinky little moraine over here because so much of the ice was melted here and rushed down, and we will see in a second the different levels of terraces down here that resulted from this. And this thing puzzled to me till it came. I had written something about this. This was a place where I got as a vista point in the book. And I was rereading, I hadn't figured all this out yet. And I reread about the hot spring pool is snuggled up against the north lateral moraine. And with the help of Google Earth and all of the information on the hot area here, it was obvious what had happened. This is a LiDAR of the area with north at the top, I guess. And not I guess, it is. This red arrow down at the bottom is pointing to a fault scarp in the Bull Lake moraine. That Bull Lake moraine is offset 120 feet by that fault. So this is still an active uplift. And it didn't happen in one earthquake. It happened in probably earthquakes of 6 to 20 feet, or maybe 3 to 20 feet at a time. So a recurrence of earthquakes through time. There's the Bull Lake moraine. Here's the fault going across. There's the hot thermal area, and here are the Pinedale moraines on LiDAR that show up so beautifully. And you can see, and we'll see a cross section through here. You can see all these different levels of terraces. As you go down, I think those are related to the smelting cycles probably. Erratics, that's where boulders are left on pavement that they don't belong. This is a granite, the Estes Park granite up in the Rocky Mountain Park, and this is a metamorphic rock sitting on top of it. And this is, you can look at it end on here. Doesn't belong there. This one doesn't belong there. These don't belong there. These are, erratics are just boulders that are out of place. They are from some other area, and they've been transported and let down. It's possible, I think, that water may have cleaned out the finer material in between these and left the larger boulders, but this is near Alberta Falls in Rocky Mountain National Park. So ice melts, and this meltwater runs out, and it forms a big outwash plain downstream. And guess what is here? All this loose debris that got dumped. The loose debris of the moraine, the loose debris of the ground moraine, of the end moraine, all of this material is very, very erodible. So as this stuff erodes out, it's usually pretty erodible. Sometimes, like there's a place in Rocky Mountain Park where you haven't been able to cut down through it because it's all these huge boulders that the modern streams can't move. And so they are trapped behind in the moraines. So we form what's called an outwash plain downstream from the moraines and the glaciers, proglacial feature. And outwash plains and terraces are the things that form in front of glaciers. And the fine material that's deposited in these outwash plains is picked up by the wind and carried off and deposited in other places for lust. So, for instance, there are huge lust deposits in Mississippi that were from the continental glaciers that got down to southern Indiana and southern Illinois and deposited their stuff, but the lust was picked up and deposited quite a ways distant from that, and that's, we'll see in a minute, a situation that we have in Colorado. So this is a view of an outwash plain in Alaska, and you can see this braided stream. Here's definition up here if you want to read that while I'm talking. And the main thing is that you have these bars of gravel, cobbles, sometimes even boulders, small boulders. And in between, there are these meandering stream lower areas that they've got a much less velocity, and so they're depositing finer material in these little areas. And this is kind of a close-up of something like that, gravel bars and the streams going through and carrying fine material at a lower pace that it's dropping in between the gravel bars. So you can see we have these high areas that were deposited at high water, and as the stream declines, you have these bars left. And you notice the shapes of them, they're kind of tapered. Well, this is an area near Durango in an outwash plain that Mary Gillum taught me about, and I'm very grateful to her for that. As you look out in this plain out here, it's very flat out there, except where the stumps of the pines are. But you find these accumulations of boulders, rounded boulders. And then you have the areas in between where there are virtually no boulders at all. We're starting another one down here. You can see the boulders. There's one over there. There's another one down there with, this is called bar and swale topography. And if we look at it from above, we find that you can see these shapes. The LiDAR beautifully shows through all those trees, and we would find on these things those clumps of cobbles and boulders. And we'd find on this one, and then the swales in between are where there would be fine-grained material. This is also a roche montagnais that's sticking up through there. So when the glacier was over this and moving down toward Durango, it was sculpting this bedrock, and it was high enough that when the outwash plain was deposited, it was left there. And you can go there, you can drive on this road and see it. So here's an Alaskan analogy for what it looked like as the Animas River Glacier, or I visualize as is what it looked like when the Animas Glacier had retreated back from Durango, maybe 14 or 15 miles back past north of Baker's Bridge area, if you're familiar with the area. And here what we have is a bedrock drop off right here. The glacier is flowing over that and it's melting. And here's all this outwash plain, and you can see all of the bar and swale features there. And it's pouring into this lake, and this one isn't even a pretty turquoise, probably because it's a cloudy day, but it's full of this silt and material that's going to settle out on the bottom. And here it's just beginning to cut through the terminal moraine down here. And so I visualize, and Mary certainly taught me this, that we've got here's Durango down here and the youngest terminal moraine. And there's Baker's Bridge north of there, and there's a big escarpment here in the bedrock of about 150 feet. And we know from the cosmogenic dating that the glacier had retreated to about this point from its maximum extent down in town. So there's the glacier that was melting and sending out this previously abraded stuff, an outwash plain. And this was a braided plain that we just saw in the pine trees. And then the meltwaters were dammed by the moraine down in Durango and backed up this former Lake Durango. So we had essentially the same thing that we had going on today in Alaska, that an outwash plain feeding into a lake. And the sediments that were going into the lake were filling the lake up. And you will end up with a flat bottom floor eventually. So here's an area downstream from Mount Princeton, and you can see the same thing out in the field here, little clumps of boulders, fine-grained stuff in between, another little clump of boulders, another little thing, and the shapes of these are the same as what we see in Alaska. And here is looking at that on the LiDAR, and you can see all of these little things preserved in the Pinedale outwash plain here. And that's what an outwash plain looks like, this bar and swale and gravel bars, where the bar name comes from. Each of these little high areas you go to, there'll be clusters of cobbles and boulders. And that's the Pinedale outwash terrace. Up here is the Bull Lake outwash terrace. And you can see they're not nearly as well preserved as they are out here, but you can see the overall back in here of these bar and swale features. And that is 55 feet higher, this plain, than that one. Because remember, the glaciers are always, each successive period cuts deeper and wider. So this is the Pinedale outwash terrace. And the other thing about these outwash terraces is they grade to the moraine of the glacier that was melting to feed all the water to the outwash plain. Today, the rivers are gone and we just call them outwash terraces. Here's the Pinedale moraine, and this terrace grades right up to the base of the Pinedale moraine. Now here we have a Bull Lake outwash terrace. That's that 55 feet higher than this one over here. And when we look across at it and back to these moraines, this is the Bull Lake moraine back there, and it grades to the base of that. And this is just kind of a 3D of the LiDAR looking. Here are the terraces cutting down to the modern stream level here, the Pinedale outwash terrace and the Bull Lake outwash terrace looking toward the east or down valley. And here we get to confusion. We're back home at Ouray, and the glacier that's coming down and stopping at Ridgeway. This is a view from Log Hill Mesa. There's a beautiful, nice little picnic area up there that you can look out on this scene, and it's quite informative and quite fun to look out from up there if you can find it. It's not easy to find, but it's up there. And what we have is kind of a outwash plain back in here, and the U-shaped valley back here that is so spectacular in the Ouray area. And we have truncated spurs and triangular facets that are left from that truncated. There's a spur that comes down and it goes into this triangular facet right here. So we know that the glacier came down here and it's going to deposit in a moraine. The question is, where is the moraine? Well, here's a moraine right here. And it's very interesting to kind of follow this one around. And there's another older moraine, and it's higher than this moraine here, the base of it is. And here's the oldest moraine, and the base of it is much higher than this one and higher than this one. So we're getting the youngest moraine. We're coming down in elevation just like we were in Durango and just like we should according to glacial models. Here's the LIDAR of that moraine, and you can see that it's quite nicely defined here. It goes right behind the school over here and then down to this bike path where we'll take a look at it at the bike path here and crosses the valley and goes on up the valley. So I stopped here on this little road to take a picture of the moraines over here. And what I saw here was, and this is all moraine, all of this area here is end moraine. And here were yaks loving the moraine, and you can see all the cobbles scattered in between the yak droppings here. And looking back over here, here's the lateral moraine here and over here. So you can really follow this thing around quite easily. And you can see what it looks like. As you can see, it looks like a lateral moraine ought to look like, and the bike path here that gives you an easy access to this exposure down here. Now, I'm not going to go into this because it's too esoteric, but I'm going to just point out that there's a published paper on this area, and each of the moraines, this is the highest moraine, and this is an outwash plain that grades to the base of the moraine. And this is the next oldest, and the outwash plain that grades to these. These are really nice. You can see these outwash terraces grading to these moraines, really nice. And you get down to QAG 3. And you get down to this outwash plain, and it dates at 23 million years, which is supposed to be the height of the Pinedale moraine. But notice they don't have any little moraines on there. This outwash plain dates to the time of early Wisconsin. So we thought, well, we've discovered early Wisconsin moraines, because this moraine that grades to that is this moraine. Yet we just said that was Pinedale. And if this is Pinedale, there's no moraine here that fits it. And the question is, where is it? And that's a huge, huge question. And still, there needs to be a lot more work done on this to resolve whether this moraine that we saw is early Wisconsin in age or whether it's really Pinedale in age. Okay, so the Aeolian deposits are things, progradial deposits. They're not really like outwash plains, but they're because of the glaciers out in front of it. So what happens, these are the glaciers on the east side of the Continental Divide in the Front Range, and they're feeding all this stuff out, and they're carrying huge volumes of sediment out here on the plains to Fort Morgan and Brush, and depositing all of this along the floodplains of the South Platte River. So you're feeding all this stuff out onto the plains. So you have these rivers that are choked with sediment with all of this sand here. And of course, it's good at winnowing. And the wind comes along after the floodplains have dried out, and it mobilizes the sand into sand dunes. And so there are huge sand dunes out here, as well as loess deposits. This is one of the big dune field that's near Fort Morgan. The wind direction, these are all parabolic dunes. They have these rounded noses, long tails that come off. This is an area east of Colorado Springs. The LIDAR showing, this is out the Ray Dune Field. And the Ray Dune Field here, you can see the wind direction probably a little bit off there. I'll probably be tilted to the left a little bit. But the wind direction mobilized all of these dunes out of the South Platte River, carried them down. And the Ray Dune Field's about 5,000 square miles in area. This is just east of, about 40 miles east of Colorado Springs. And you've got the same thing here. And you see these little noses here on the parabolic dunes. And these long tails get left there. And a lot of people initially misinterpreted these as longitudinal dunes rather than parabolic dunes. But these dunes are kind of like the wind direction going this way. They're kind of like a bobby pin. And I know that some of you are old enough to remember bobby pins. If you notice the comparison of that to this over here is quite similar. Okay, Lurs. Funny story about Lurs. We had some German directors on our board for one of the companies that I worked for, and they would annually like to have a meeting at a fancy place where there was good golf to play. And they were trying to decide where one is. And this German said, why don't we go to Phoenix? They have lots of golf courses there. Of course, that's the pronunciation. Phoenix, that's the way we say it. At any rate, this is about the common thickness of loess out on the plains. This is just fine-grained sediment, has a lot of mechanical characteristics in it, and this is about a 60-foot high loess deposit out near the Kansas border. So the aeolian deposits out on the plains, this is the whole state, and these about 70% of the deposits that are wind blown out here are loess, and about 30% is dunes. And the total area covered by these wind-blown deposits out here are 30,000 square miles. Now, they were not deposited, some of them were, but the majority of them were not deposited during glaciation. They were deposited after glaciation because of all of this sand that has been carried out along the Platte River and the other rivers. And we were working out on the plains, and you still get dust clouds today. This stuff's going to settle out and form loess eventually somewhere. And you get it in the snowpacks, and in the snowpacks, it's causing early melt, not really melting. The state climatologist actually told me that most of the early disappearance of the snowpack is from sublimation. So it's worse than early melting because it's not going down the rivers, it's going up into the air because of these layers in the snowpack. And sometimes you can get as many as 17 layers in some of the snowpacks that people have examined and found, and it gives you very weak layers that avalanches can slide on. So not a good thing for us. Okay, our average annual temperature here, we looked at it early on, but just a quick refresher on it. Down here in the lower right of the state, we were averaging about 55 degrees for our annual temperature for this 30-year period. You can see the purples where we are getting into less than 35 degrees, and that's very close to freezing. And going from south to north, we're going from fairly warm down here and getting cooler as we get up. We wouldn't call it cold, but certainly cooler, as we should on the Earth. In general, we go north toward the poles, higher latitudes are colder average temperature. And our cross section again going through this. And we had permafrost out here, which we're going to talk about in a little bit. So this is a long temperature record up at the NSF-sponsored Niwot Ridge Research Station, which was operated and started by University of Colorado, and it's now an international alpine study station. And they have a temperature gauge that's been there since 1952. And It's at an elevation of 12,264 feet. So that's the average temperature for this long 70-some period. And the assistant state climatologist did this little, make it a little bit simpler and do annual averages. And you can see that the average here is a little below freezing. This is centigrade scale here. So we were about -3. And the average that you get from the daily things is -3.5 from the temperatures. The farther you get away from the actual readings, you're getting a little bit different, but at any rate, it's close. -3 is well below freezing. So this fits the conditions for permafrost. Okay, the above ground features that have to do with cold, we have permanent ice patches, we have these little glaciers, and we have rock glaciers, which we're going to talk about the rock glaciers. We've talked about these on the first day, okay. And below ground, we have permafrost and we have frost action going on associated with the permafrost, or maybe not associated with permafrost. So to define permafrost, it is ice that's been in the ground permanently for 2 years, hasn't melted during the summer at all, and the annual average temperature of the area that the ice is in the ground is 0 degrees. So we got -3 degrees, that's certainly within them. And the frozen permafrost, we saw the definition of it. So this stays frozen. But the upper part of the frozen is what's called the active layer. And this active layer actually melts during the summertime. And that gives us all kinds of wonderful little decoration on our glacial landscape in Colorado's mountains. Okay, so frozen for 2 years, and then we get frost action in the active layer. So one of the things that we get from a result of these cold temperatures are rock glaciers. And the rock glaciers are all pretty much above 12,000 feet in terms of where they form. This was a count that was done by the Portland State University Geography Department. They got over 4,000 rock glaciers. That's double the number that Idaho, which was the second, had. And it is the majority of the rock glaciers in the Western US. They analyzed 10 states for rock glaciers. And this is what one looks like. This is the Imogene rock glacier out from Ouray. You couldn't ask for a better example than this. This is just absolutely magnificent. And there are lots of features about this that are just really cool. So the first thing is that rock glaciers have these furrows. You can see them all the way up here. Before we knew anything, this told us that this mass of rock was moving or had moved at one time. Initially, these things in the San Juans were interpreted as big, massive landslides that flowed out instantaneously. But we now know that that's not really the case for these. And this is a wonderful example of some things that go on. You notice that there are levees along the side there, these raised areas. And most rock glaciers have those levees. They're very characteristic of them. They have a steep front. And notice that the lighter colored rock here on the steep front versus above that, that means that the rocks are being turned over and they're not getting lichen developed on them. And this light, that's one indication that this is an active rock glacier, that it's actually still moving there at the front. There's some other things that tell us that, but this is the motion that we have down there. There's an upper portal to the Camp Bird mine up here that was, this added was drilled back horizontally in 1899. And at that time, the rock glacier wasn't over it. And the rock glacier moved over this old adit, there, this old adit, and caused it to collapse, almost completely collapsed. So that only Rick would be the one to go in there these days. And this new portal was drilled in 1987, or cut in 1987. And it's since had some problems from the weight of the rock glacier coming over. Moreover, there was a very forward-looking person back in 1970 that painted rocks across this. And some very dedicated folks in Ouray have gone out and looked for those painted rocks and recorded where they are. And this is just wonderful that they've taken the time to do this. And it shows us that the ice has moved about 90 feet since it was painted, or about 2 feet per year. So one model, there are two kind of end members of these rock glaciers. One is that you had a glacier or ice core pre-existing, and that talus fell down from the steep head wall of the cirque that these things form in, and most rock glaciers form in cirques. And the rocks just covered this pure ice core. The other model is that these are ice and rock, and also a cover of rock on top, but that it's this interstitial ice that forms in the talus and then moves out as a rock glacier. And this is still a pretty strong debate here. I'm actually involved in one right now on this. Here's a rock glacier, east of Leadville. This is about 135 feet high here. It's a beautiful place to go take a little hike in the springtime, i.e. end of July, and get all the beautiful columbines and other flowers in the cirque, and see a cirque and see a rock glacier up close and personal. And you can see that there's a little bit of layering, rough layering in that. And at the front of it, this is somebody who took one of my courses. And one of the things that I encourage you all to do is to let me know when you find cool stuff, because this was a guy who had taken one of my courses in Leadville, and he and his wife went out and they found where in the springtime, when the ice, presumably we were getting ice that was melting, this rock glacier had moved out and plowed up the turf. So we know that the front of this thing is actively moving. And I've had people that have taken courses that'll send me things, cool things that they find around the state, and I certainly encourage you all to do it. And here's your Hurricane Basin rock glacier that is about 8 miles east of Ouray. And it had an adit right here that a drift was driven back through the rock glacier itself for about 300 feet and was recorded. And what we found was that in the first 300 feet or so, you found ice bound by rock, or rocks bound by ice, which would fit the model of interstitial ice for a rock glacier. But for the last 100 feet, it had plain ice. So it would confuse the debate about how these things form. And I think I'll leave it right there, and we will talk about Pyramid Peak and other stuff next time. I'll hang around a bit if there are any questions right now.
Thank you so much, Vince. We do have a looks like just one question and a comment on our chat. The question is from Pete. Pete asks, the nice glacial valley and the moraines that Vince was talking about, that in quotes, you don't have to fight crowds in Rocky Mountain National Park to see. They missed what valley that was.
It's the Woods Valley, and it is between the Rudai Reservoir and Sylvan Lake State Park. And Sylvan Lake has a great view of red cirques and red moraines. So coming out of Eagle to the south and stopping in Sylvan Lake and looking at the moraines and the cirques, and then driving up over the hill, you will go by Woods Valley Glacier. It's a little turnoff it's a good gravel road that's well maintained, or was well maintained. Can't swear to it now.
Perfect. Lou asked, where is Bull Lake?
It's on the front side of the Wind River Mountains, the southwest side of the Wind River Mountains, as is Pinedale's near there also. Pinedale's a very famous gas field now.
And feel free to unmute yourselves if you had any final questions.
I'm trying to find out where things are. Oh, stop that. There we go. Now I can see you all.
Well, I guess you left him with a lot to think about. We've got a quiet class.
Hopefully it didn't overwhelm. No, there's a lot of smart people here that I see here. This is just a review for them. Anything? Hi, Lynn.
Hi, Lynn.
Hi, this is Pete here. Do you hear me?
Okay, sure.
Yeah. Something that interesting that sort of an aha moment insight that came to me at the very beginning of your talk when you were talking about moraines and showing a diagram of them as a conveyor belt, and of course later as a dump truck or a bulldozer, that one of these things that I just never thought about, you know, not being a person who thinks about glaciers all the time, right? That if a glacier is advancing, if the front of the glacier is advancing during a cold period, and of course the glacial ice is still moving, that any of the glacial debris, the rock debris that gets dumped at the front of the glacier from the melting that takes place there is just going to get re-picked up by the glacier and carried on down. So those rocks are going to, they're not being deposited, so they're just getting tumbled and carried and scraped and crushed over and over and over again until they finally end up in a terminal moraine someday somewhere. It's just sort of an insight that I never, does that sound right?
It definitely is, Pete, and there's a lot of complications. Those end moraines are extremely complex, and trying to figure out, you know, exactly what's happening there is a nightmare for people who study this sort of thing, or for us looking at it, trying to imagine what happens. So one of the models of this, and I'm sure they're based on observations in other places where glaciers are still active, is that you get actual thrust faults of both the glacier at the front and of the moraine that's been deposited in front of it. So it really gets complex, and there can be some overriding of it also. But just think about it, if you override, let's say, an end moraine, and you've got all that thrusting, and then you come back and you are depositing right there on top of all that, you obscured most of the stuff. I mean, it's really hard to sort out in this kind of regime what's actually gone on in the past. And I would say for most of us, about all we can tell is, and most glaciologists in most places, as an end moraine. And
Yeah, thanks.
And there's
Vince,
one, Camp Hale recessional moraine is interesting, and we'll look at that. And I wasn't going to talk about it, but it complicates it. But I showed you the till of these cobbles and boulders in the up valley part of it. But as you drive through the road cut at Camp Hale of this recessional moraine, it suddenly abruptly changes to all sand. The landform itself goes from, and it's almost like a sharp line, like somebody drew it with a knife. You just go from this pile of cobbles and everything into sand.
Vince, this is Lou. Can you share, or would you like to share where your experience and knowledge has led you to be amazed at the application to other locations in our solar system?
I'm not sure I quite understand that, but Lou, I'm certainly interested in what's being found on Mars, but I haven't really tried to keep up with what's going on most of the planets, because I think this planet's so fascinating and there's so much I don't know about it that I want to focus here.
Okay, no worries. Thank you.
You bet.
Vince, this is Ron Parker. I have a question for you.
Sure.
I joined the session late, so perhaps you spoke about this. I don't know. But I used to live in Vermont. And one really cool thing to do in the summers in Vermont is to go swimming in rivers and find great big potholes. And there's a place in Bolton, Vermont, Joyner Brook. It's this little tiny creek running over bedrock that flows through an 80-foot pothole. It's gigantic. And there are also potholes that they find on the top of ridges in Vermont, in the top of the mountains that are bored into bedrock where no river flows now. And so the supposition, of course, is that it was glacial meltwater that was falling through cracks in the ice, continental glaciers, that were over the tops of the mountains that, bored these gigantic boreholes. Anyway, do we find any of these in Colorado? Large potholes that have underfit streams going through them that really could only have formed by deglaciation meltwater.
I'm not familiar with any here. I have seen what you've described in Canada and in Wisconsin, and they actually, I think, have witnessed that these things during flood stage, they'll get these big boulders and cobbles in there and they'll just spin around and essentially drill these potholes down. So that there are all kinds of things that happened under glaciers that we don't really understand completely because it's, again, hard to observe down there. I have seen, in fact, Bob Anderson at CU showed a picture beneath the glacier where there was actually the plucked end of a roche montagne that was being sculpted, and you could see the ice sitting on the abraded part, but it was melted away on the downside, and you could see where the stuff had been plucked out of it. He gave a talk to the Colorado Scientific Society last year that he showed that image, which, they're going to be limited what we see underneath there. But
Okay,
I
thanks.
think the idea, they found a lot of these potholes that actually have the boulders still in them that were part of the grinding, at least during one phase.
Okay, thank you.
Last call for questions. Well, thanks everybody for joining us, and thank you so much to Vince. That was a really fantastic presentation.
Thank you, Vince. I enjoyed it.
Thank you, Lynn. I appreciate your comment.
It's let's see, April 3rd. Next week, April 3rd, 10 a.m. So we'll see everybody next week.
Okay, look forward to it and really
Hey.
appreciate everybody's interest in this.
Vince, you're